Okay, so there are different types of solids. We talked about amorphous versus crystalline. A crystalline solid has order to it. An amorphous solid is just sort of random particles lumped together. We can take those crystalline solids and divide them into three categories based on what are the individual particles in that solid. So it could be molecular, ionic, or atomic. So molecular solids are going to have molecules, hence the name. Ionic solids are going to have formula units. They're going to be ionic compounds. They're going to have cations and anions. And atomic solids are by nature elements, and their composite units are atoms. So knowing what the particles are, we can predict melting points based on what we know about the strength of the intermolecular forces that are attracting these together. So molecular solids are going to have low melting points because these are held together by intermolecular forces. Ionic solids are going to have very high melting points. They're held together by ionic bonds between cations and anions. Atomic solids have atoms in them, and these are going to be very variable. Considerably variable. There's a lot of difference. Very variable isn't a good way to say it. Anyway, there's considerable variability in the melting points because what holds atoms together? The dispersion forces, right? Dispersion force is the only force of attraction between atoms. So the dispersion force depends on the size, and if you look at the elements, the sizes vary a lot, and so that has a lot to do with the melting points. I'm going to go through this part quickly because I've already said most of it, and you can read it. Molecular solids, such as dry ice or solid water, tend to have low melting points held together by intermolecular forces. Ionic solids held together by ionic bonds are going to have high melting points. Things like sodium chloride melts at 801 degrees Celsius. Atomic solids. Most atomic solids are just atoms attracted by dispersion forces. So those are the non-bonding. They're held together by dispersion forces. These tend to have low melting points. Covalent atomic solids are essentially a giant molecule. The whole solid is one molecule. The atoms are actually bonded to each other. Silicon is an example of this. Diamonds are an example of this. Those are going to have high melting points. We can also have metallic atomic solids where the atoms are held together by metallic bonds, and those can vary considerably in strength. Yeah, please close the door, yes. They're kind of loud out there. Despite the signs that say, quiet please, classes are in session. Thank you. So covalent solids held together by covalent bonds. There aren't very many of these. These are somewhat rare. Diamonds are an example. A diamond crystal is essentially a giant molecule. Carbon atoms covalently bonded to each other. It'd be like this. So the carbon atoms, they're just covalently bonded all throughout the diamond. Non-bonding, solid xenon is a non-bonding atomic solid, just held together by dispersion forces, so really low melting points. Metallic atomic solids, these would be the metals. The temperature of melting can vary. Mercury melts at minus 39 degrees Celsius. Iron melts at 1809 degrees Celsius. So what is a metallic bond? The simplest model is called the electron C model. And so again, I think of electrons as being like little boys. So here's a neighborhood, and here are the homes on the neighborhood. And they've all got a little boy here, the electron, and they send the electrons outside to play because the kid's getting squirrely and bothering mom. Go outside and play. So the electrons go outside and play, and they're roaming all over the neighborhood. This is how things were when I was growing up. All of these little boys out here causes the neighborhood to be very close because the moms watch out for the other kids, right? Because they know, oh, that's so-and-so's little guy. And so they keep an eye on each other, and it bonds them together. So that's the analogy one. More scientific is, so we've got these electrons that are free to move. We call this the electron sea. It's like a puddle of electrons here. And so we have this negatively charged sea of electrons, and that is attracted to the positive nucleus and vice versa. And so that's what holds those metal cations in this negative sea of electrons. It holds them together. So that's all very nice. This is the sort of question we need to be able to answer. Identify each as molecular, ionic, or atomic. This is actually much easier than it may sound. Is it an element? Is it an ionic compound? Is it a molecular compound? So if it's an element, there's only one capital letter. If there's more than one capital letter, then we have to ask ourselves, is it molecular or ionic? If it has a metal in it, it's probably ionic. So if we look at this one, NH3, that's a compound, right? Not an element. It's got two nonmetals, so it's a molecular compound. That means it's a molecular solid. So we'll just put M for molecular. What about this one? What kind of an element is calcium? This is ionic, because calcium is a metal and oxygen is a nonmetal. So it's an ionic compound, it's an ionic solid. Krypton. That would have to be atomic. Any questions?